Hello, this is a number theory video on the Chinese Remainder Theorem. Before we get to the Chinese Remainder Theorem, I'd like to look at divisibility and a quick little proof. Let's go to our week 12 handout. Number theory is a lot about divisibility, and divisibility is a lot about remainders. We do remainders almost every week in this course, and we look at it from different points of view. So here is kind of a random example that I want to use to make a point. I want to simplify 435 mod 8. So mod 18, excuse me, I'm looking for a number 0, 1, 2, 3, up through 17, which is the remainder when we're dividing by 18. So what modular arithmetic does is gives the remainder when you're dividing by the mod. Now, let's say that you've got a calculator and you want to save yourself a little bit of work. If we run this into a calculator, we get 24.16 with the 6 repeating. So this is kind of the thought bubble. So it goes in here a total of 24 times. 24 times 18, which I'm also going to do on a calculator, is 432, which leaves a remainder of 3. Therefore, 435 is congruent to 3 mod 18. I just wanted to show that example to make sure we're making the connection. Now I would like to prove the following theorem. This is an existence of inverses theorem. We have a and m, which are integers. Of course they're integers. This is number theory. And m is going to be a modulus, which we like to be a positive integer. I want to solve ax is congruent to 1 mod m. In other words, I want the inverse of a so that when I multiply them, I get 1. This has a solution if and only if a and m are relatively prime. This is a nice proof because it uses our definitions and our idea of a linear combination. Proof. And I'm going to do this as an if and only if, so it goes both directions in one fell swoop. Ax congruent to 1 mod m. Let's see what that means by definition of congruence. It means that m divides ax minus 1. Now, what does this mean? By definition of divides. If and only if there exists k in the integers such that mk is equal to ax minus 1. This is our definition of divides, which we've used throughout the course. And now, if I do a little bit of simplifying here, rearranging terms here, if I add 1 to both sides and subtract mk, I get 1 equals ax minus mk. And then I think I'm going to use the symmetric property to make this ax minus mk equals 1. So I have a linear combination of a and m that gives 1. This means that a and m are relatively prime. And the reason for this is because we wrote a linear combination of A and M that is 1. Because we wrote a linear combination of A and M that is 1. And since 1 is the, sorry, just a second. Since 1 is the smallest positive integer, this is the greatest common divisor. So all of these are if and only if. So if I would have started with A and M being relatively prime, I could have written the linear combination and gone up the chain. Okay, now I'd like to give you a little bit of a sense of what the Chinese remainder theorem does. Here's an example of a problem that I had on a test a few weeks ago. A woman with a basket of eggs finds that if she removes eggs from the basket 5 or 7 at a time, there's always 1 egg left. However, if she removes eggs 9 at a time, there are no eggs left. If the basket holds up to 100 eggs, how many eggs does she have? So you might try to solve that problem now or later. Here's a slightly more sophisticated question. We use the Chinese remainder theorem to solve the following. Find a number that meets the following 3 conditions. When divided by 5, the remainder is 2. When divided by 8, the remainder is 4. When divided by 11, the remainder is 5. Now, let's just think about that last bullet as an example. When divided by 11, the remainder is 5. So it might be 16, or 5 more than 22, which would be 27, or 5 more than 3 times 11, which would be 38. It's 5 more than a multiple of 11. Okay, now let's go over to our textbook and take a look. Here we are in section 3.4, and I'm going to let you read this on your own. A couple things I want to note, though. Our authors decided to use n's for the moduli rather than m's. Not quite sure most authors would use m's, but since our author is using n's, I'm going to use n's. The lowercase n's are the separate moduli. Capital N with no subscript is the product of all the little n's. Now, all the little n's have to be pairwise relatively prime. So if you take each pair, n1, n2, n1, n3, and so on, they have to be relatively prime as pairs. That's a pretty strong condition, but that will always be the case. We also have some cap n subscripts, cap n sub 1, cap n sub 2, and so on. And I'm going to show you how that all works in an example. Our author has worked out an example 31 here, and this is a good example, and they've worked it out correctly. The answer is 23. I'll let you study this on your own. One thing I will note here, down here in the bottom line, these look like decimal points, but it's actually multiplication. It's 1 times 15 times 1 and 2 times 10 times 1 to give 53. And then 53 is simplified to 23 because we're mod 30. The mod here is the product of the mods. I know that's a lot going on. This is why we need to have an example. Now let's go to the Chinese Remainder Theorem handout. Okay. I'm going to show you the method for 3 congruences, but this can be simplified to 2 congruences or generalized to more than 3 congruences. One comment I wanted to make before I forget is you might be wondering, what are some applications of the Chinese Remainder Theorem? My goodness me. A lot of the number theory that we're learning is applied when we want to do encoding and decoding. Encoding theory is something that's very important. It used to be important back in the Cold War and World War I and World War II, because we wanted to have coded messages to send to our troops, but we didn't want them to be intercepted and decoded by the enemy. But it's become even more important in the age of DVDs and the internet, because we're often sending messages over a wire, whether it is an email, a streaming video, or whatever, and it's often encrypted on one end and then decrypted on the other. So there are many applications of number theory in electronic communications. Okay. On the left side of the sheet, we have the general theory, and on the right-hand side of the sheet, we're going to do an example. So I'm going to do one with 3 congruences. So my first congruence is x is congruent to 2 mod 5. So I can see that B1 is 2, N1 is 5. My second congruence is that x needs to be congruent to 4 mod 8. So B2 is 4 and N2 is 8. And the third one is x is congruent to 5 mod 11. This is the example that we're going to solve today. First thing we do is we calculate n. N is the product of the moduli, 5 times 8 times 11, which is, use a calculator, I believe it is 440. Yes, 40 times 11 would be 440. Now I calculate the N1, N2, and N3. Now, an easy way to think about this is N1 is N with little n1 removed. So I have 5 times 8 times 11 with 5 removed. That's 88. Cap N2 is 5 times 8 times 11 with 8 removed, which is 55. And cap N3 is 5 times 8 times 11 with 11 removed, which is 40. It's very important that you are clear on your capital N's and your small lowercase n's. This is typical of notation in mathematics. We have to write things carefully. Now I need to solve 3 congruences. And the congruences are right down here. N1, Y1 is congruent to 1 mod N1. N2, Y2 is congruent to 1 mod N2. And N3, Y3 is congruent to 1 mod N3. They're always congruent to 1. So the first one I need to solve is 88 Y1 congruent to 1 mod 5. Now 88 is a ridiculously large number, so I'm going to simplify 88 mod 5, which we've been doing for about the last 2 weeks. 88 is the same as 3, because when I subtract multiples of 5, I'm left with 3. I'm in mod 5 right now. Three times what is congruent to 1 mod 5? Now, there's only 5 possibilities to check, 0, 1, 2, 3, 4. And as we check these, and you might pause the video if you want to try to find y1 on your own, y1 turns out to be 2, because 3 times 2 is 6, and 6 is congruent to 1 mod 5. So y1 is 2. My second little problem to solve here is n2 y2, 55 y2 is congruent to 1 mod little n2, which is 8. First thing I need to do is get 55 simplified. Well, the largest multiple of 8 less than 55, I believe, is 48. 55 minus 48 is 7. So we have 7y2 congruent to 1 mod 8. And then if I consider my possibilities here, I want to get something 1 larger than a multiple of 8. I believe that's going to be 7. y2 is congruent to 7 mod 8. Because 7 times 7 is 49, which is 1 bigger than 48. My third congruence is going to be n3, which is 40. y3 is congruent to 1 mod 11. So I need to simplify 40 mod 11. 11 times 3 is 33. 40 minus 33 is 7. So we have 7y3 is congruent to 1 mod 11. And now I test out my possibilities, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I believe that y3 is 8. Because I get 56, which is 1 bigger than 55. So now I have all the raw materials for my solution. I need my B values, my cap N values, and my Y values. So X is congruent to, okay, B1 is 2. N1, 88. Y1 is 2. If you can be one step ahead of the professor, I encourage you to do so. B2 is 4. N2 is 55. And Y2 is 7. B3 is 5. N3 is 40. And Y3 is 8. So we have 352 plus 1540 plus 1600. By the way, this is mod 140. Adding these all up, I get 3,492 mod 5 times 8 times 11 is 440. Mod n. Now I just need to simplify this. So let me scroll down here and get myself a little bit of work. This is the work which you may or may not put on your paper. If I divide by 440 and do this on a calculator, I get 7.936 with the 3/6 repeating. So apparently this goes in here 7 times. 7 times 440 is 3080. And when I subtract, I get a remainder of 412. So X is congruent to 412 mod 440. So apparently 412 is my answer. Now, one of the things I want to make special attention to is we probably did not expect an answer like 412 to the original question. The original question here was we wanted an X value that was congruent to these 3 numbers in these 3 mods. The answer is 412. Well, let's check it. 412 mod 5 is 2. 412 mod 8 is 4. That might require a little bit of work. And 412 mod 11 is 5. That might require a little bit of work as well. Put a box around your answer. Okay, now I'd like to actually do a couple easier examples. This example just has 2 congruences. X is congruent to 2 mod 5, and X is congruent to 4 mod 9. And we're going to kind of do this one more from first principles. We could use the Chinese Remainder Theorem on it, but I'm going to do this one from first principles. My first congruence here, this is going to be 2 plus any multiple of 5. This is called equals. T is an integer, of course. As we saw with the Chinese Remainder Theorem, we might get an answer that's larger than 5 or larger than 9. So let's list the X values that work here in this first congruence. They are 2 plus 5, which is 7, 12, 17, 22, 27, and so on. And then what I do is I start testing these to see if any of them are congruent to 4 mod 9. You might pause the video and see which of these numbers is congruent to 4 mod 9. Well, 2 is still 2 mod 9. 7 is still 7 mod 9. 12 would be 3 mod 9. 17 is 8 mod 9. 22 is in fact 4 mod 9 because it's 4 bigger than 18. So my answer here is that X is congruent to 22 mod the product 4 times 9, which is 45. The last example I would like to do is more of a word problem. This is similar to the homework that's going to be out of the book. We're supposed to find a number such that the remainder is 5 when we divide by 8. And the remainder is 2 when we divide by 9. Find a number that leaves a remainder of 5 when we divide by 8 and a remainder of 2 when we divide by 9. So what's this equivalent to? This is equivalent to x is congruent to 5 mod 8, and x is congruent to 2 mod 9. And I think I'm going to go ahead and use the Chinese Remainder Theorem method rather than the first principles method. So, looking at our notation here, B1 is 5, B2 is 2, little n1 is 8, little n2 is 9, and 8 and 9 are relatively prime. So I'm going to calculate n. That's 8 times 9, which is 72. Cap n1 is 8 times 9 with 8 left out, which is just 9. Cap n2 is 8 times 9 with 9 left out, which is 8. And now we need to solve n1, y1 is congruent to 1 mod small n1. That is, we're supposed to solve 9y1 is congruent to 1 mod 8. You might pause the video and see if you can do that. The next equation I need to solve is n2, y2. Okay, actually I haven't solved this one yet. y1, 9 times y1. Well, 9 is 1. So we have 1y1 is congruent to mod. And so y1 turns out to be 1. That's okay. The other congruence I need to solve is n2, y2 is congruent to 1 mod 9. And testing out all my possibilities, the y2 value that works is 8, because 8 times 8 is 64, which is 1 bigger than 63. So now I'm ready to plug in to get my x value. X is congruent to B1, N1, Y1. 5 times 9 times 1 plus B2, N2, Y2, which is 2 times 8 times 8. This is mod 72. Adding these up, I get 172 mod 72. And if I subtract 72 a couple times, I get 29. X is congruent to 29 mod 72. Let's check it. If I take 29 and put it back up here, 29 is congruent to 5 mod 8. And when I put 29 up here, that is congruent to 2 mod 9. We do want to write the answer in this form. It's kind of odd that we would write the answer in this form because we were working with mod 8 and 9 to begin with. The reason we write it in this form is this would give us other answers. So 29 works. 29 plus 72 would work, which is 101. Add another 72, and we're back to, I think I've got a small mistake here. Yes, I do have a mistake. I wrote down the wrong number from my calculator. So let me fix the 172. It should be 173. $173 works. You could put 173 and add another 72 on that. All of those are going to be solutions. This has been a video on the Chinese Remainder Theorem. Any student taking a number theory class should do the Chinese Remainder Theorem. And school children should also do the simple little Chinese Remainder Theorem questions, like taking groups of eggs out of a basket. They're not going to be using the same algorithm we are using. They're just going to be thinking about multiples. Have a great day.